Hey YouTube! So, after my last video about the TE3AC charger that exploded, that my friend owned, and doing a teardown and analysis of how that's designed, I was actually curious how this charger that I've been using for the last 2 years is designed, and really how well it's built. What's the build quality behind this, this product? I've had a couple balanced chargers before, and you know they're kind of, I wouldn't say hit or miss, but you know they're also designed to a price. So this is going to be a teardown review, not an actual functional review of the menus and the buttons, etc. So on the outside we've got an extruded aluminum case. We've got heatsink fins on this side. AC input, universal voltage 100 to 240 volts, 50 to 60 hertz, or a DC voltage input of 1.5 amps. This bit's a little bit misleading. You can connect a DC power source here, however, it's not exactly clear what its acceptable input range is. They may have clarified the stamp on the product. They have a temperature sensor input, but they don't give you a temperature sensor, at least when I bought it they didn't. And I think the temperature sensor is only used for nickel metal hydride or nickel cadmium charge modes, because they do delta T sensing instead of constant voltage, constant current charging. And you'll have to look those up because this is more about the design and build of this. On this side we've got two banana plugs, negative, positive. They look like they're nickel-plated copper or aluminum. And we've got balance JST connectors out to 1, 2, 3, 4, 5, 6S, so we can do up to a 6S battery. And on the front we see it handles lithium cells up to 6 cells, NiCad or nickel metal hydride to 15 cells, sealed lead acid to 20 volts, at a rate of 1 to 5 amps, or a max discharge of 1 amp. Alright, so let's get into the nuts and bolts of this thing. I'm going to just start taking screws off, and hopefully I don't break my charger, because I actually like this charger. It seems to be doing me pretty well. I'd like to not break it. But at the same time, if that charger that my friend had exploded, I'd like to know if this one is poorly designed and might explode as well. It's interesting because the TE3AC crap charger, I believe only sells for about $30. However, the IMax maybe runs about $80. So if you can save up your money, it makes a lot more sense to buy this style of charger, because it lets you control and set what the actual charge current is. It lets you discharge for storage your batteries as well, where the dumb charger does not. Alright, so we just have some anodized aluminum end plates. Nothing particularly special. Oh, I missed a screw. Yep, that would help. Looks like we just have some regular self-tapping screws, lightweight, low-gauge aluminum, and oh, that is just charming. Okay, that is the laugh that I needed. Okay, so I think the way this is assembled, because you can't just, can you just slide this out? No, I don't think you can just slide this out. I think you actually have to pry this out a little bit. The board is set in such a way that these buttons, you can't just slide it out sideways. You'll notice that the big block here is just an off-the-shelf DC device, and they just put a little bit of foam tape on that side to make sure that when you press into it, it doesn't clack against the case, making you think something's broken. So, I mean, that cheapness aside, how do I get into here? I think I just pry this open a little. Yeah, okay, there we go. Yeah, there we go. There we go. Alright, so, anodized case. Heatsink fins for the off-the-shelf off-the-shelf power adapter. There's no stamp on the side, so we don't actually know what voltage this is putting out. But that is most certainly designed to a price. That is hilarious. Okay, that is one way to provide AC functionality without having to develop your own AC section of the board. Alright, let's look at the rest of this design. We have a standard LCD module soldered directly. There's no header, so I can't disconnect this without desoldering this. So it's going to be a little bit difficult to go through the rest of that review in terms of the actual design and construction, but we'll do the best that we can. Okay. Sorry, it's a little unwieldy with that. Let's take a look at the board design at a glance. And in fact, I think I'm going to try and pull this in more and give an even better macro shot from overhead. I'm recording this using the live stream setup, but I'd like to try and use the setup more live so I don't have to do editing in post. So let's just manually focus that in. Good enough for a union job. Alright, so what do we got? LCD, which they don't take the protective cover off. It is now off. I normally don't do that. Alright, what do we have? We have a array of resistors for the balancing of 6 cells. There's an unpopulated component here, a couple other components. We've got the 2 terminals, and for the sake of curiosity, are these copper or are these aluminum? I believe these are copper. Maybe brass? No, they are not. I do not see any copper color in there, so I suspect that they are brass. Alternatively, they're not steel, they're not magnetic. Though this resistor is magnetic, the terminals are not magnetic. Okay, so aluminum terminals, not the greatest, not the worst. It looks like this is a switching MOSFET in series with these 2 resistors, so they probably do voltage sensing across this resistor here, one of the 2, or both. And that's the gate on the resistor, source and drain. Oh, you'll also notice here, version 1.9, 2017-609. So this video is being filmed in 2020 in early August. So, I mean, this is a 3-year-old design. We got our temperature sensor input here. We've got the DC voltage input either through here or through here. What else do we have? Got another MOSFET. So this is a buck converter. There's yet another MOSFET back here, which is kind of interesting. I think these 2 are in parallel. It appears that there's 2 MOSFETs, one under here and one over here, that are in parallel. No, they're not in parallel. They're not in parallel, but I can't tell where it's coming from. Because this voltage input is actually in parallel with the DC input jack. So, I guess if you run the AC input through this brick, you'll get voltage on this output or this input terminal, and if you plug something in at the same time, you might blow it. So that's an easy way to measure what the voltage of this brick is providing. And if the AC functionality dies, maybe you can just power it by DC functionality and snip this off. I don't think there's any diode protection involved here, because you probably end up feeding power into this AC brick at the same time. Anyway, all that aside, looks like we've got just a little linear voltage regulator here. It looks like it's a 7805, 5 volt for logic back here. 4 push buttons, no big deal. Underneath, which the camera isn't going to be able to see, we've got a microcontroller right around here. We've got 2 identical looking arrays of resistors and transistors between all of these lines for the battery, which are also connected to op amps in the back, like the lines from each battery connected to the op amps, and the transistors, which are maybe just visible. Yeah, you can just see these transistors. There's actually 2 sets, one further back in there, that are responsible for the balancing between the different cells. So that's about all I can identify. You've got another small analog glue circuit here, probably an op amp. And that's it. It's pretty simple from this side. You've got a little buzzer, no big deal. Really loud buzzer, but then again, you want to be able to hear it. A couple unpopulated positions, but you know, a lot of electronics do have unpopulated positions for one reason or another. I'm going to try going a little deeper here, because I want to see what's on the underside of this board. Alright, so what do we have here? It would appear that we have an SEC. Yeah, we have an SEC off-branded. Oh no. Oh no, I fucked up. IRF-Z44 MOSFET, and by bending this back, I just snapped the lead on it, because look at the angle that this is soldered on. So I'm gonna have to replace this now. Oops. We had a sill pad here, and this was actually just sandwiched between the PCB and here. So the thermal conduction from this MOSFET down here is not going to be particularly great. Usually, they have 2 MOSFETs, one to regulate charge current, which I guess has lower power dissipation, because the power dissipated isn't in the MOSFET, it's in the battery. And then you've got the discharge MOSFET, which is usually bigger and heat sinked, because this is being run in a linear fashion, and it's dissipating power into the case. I believe these are just current sense resistors, and this just helps form a feedback loop. So if I just ohm across these are very low resistance. I actually cannot get a reading off of these with the regular multimeter, or the cheap one. I might have to go get the Fluke. Alright, so let's measure resistance here. 0.6 ohms and a 1 ohm. 0.9, 0.7, 0.6, Okay. So, two slightly different resistors. Probably... No, they're... What is going on there? Oh no, that's isolated. Okay, that makes sense. So... Okay. This center terminal is common to ground. The charge current comes through the battery negative terminal, goes through here, through the charge control, or the charge current regulating MOSFET, through a 0.5 ohm resistor to ground on this trace here. On the opposite side, battery voltage positive branches off to, I guess, the source on the MOSFET, the source terminal. This is the gate, drain, source. Okay, I guess this would be the drain. And then the source follows this trace up here to this resistor, and this resistor, goes over to this resistor. So positive goes to this lead, which goes to here through the MOSFET, which jumps over to this side of the resistor, which then goes to ground. So this is your drain, or this is your discharge resistor, and this MOSFET's acting in linear mode when you set the discharge current. It's not a bad design per se, other than the fact that the MOSFET's just kind of sandwiched in there and it's shitty design. So yeah. And oops, I fucked up when I disassembled this, but this is a really interesting find. The let's refocus this here. It's a really interesting find how they use this power brick as a quick and dirty way to get or incorporate AC functionality. Literally, some factory or designer in China would have just had to call up a factory and say, hey, can you send us mostly finished DC power supplies? And they incorporated that into a design. It feels lazy, it feels like a cheat, but I suppose it's a completely valid means of product design. Yeah. Now, I guess I'm gonna have to figure out a replacement for this IRF Z44. I might have replacement MOSFETs that fit the bill and are off the shelf, like in my parts bins underneath the workbench. Yeah, I feel a little dumb for doing that, but shit happens. It's a pretty straightforward design, nothing too remarkable about it. I guess the only thing that bugs me is the poor conduction between here and the heatsink on the aluminum, and the fact that most of the heat-sinking aluminum here is focused on only passively cooling this little switch mode box, which appears to just snap together, but I can't seem to get it apart. And I don't want to break something I can't replace, because they may have solvent or ultrasonically welded this, so yeah, I think I'm just going to cut my losses here, find a replacement MOSFET, and solder that back in tomorrow, because it's late at night anyways. That's it for the review, or teardown review, of the IMax B6AC lithium polymer, or intelligent battery charger. Bottom line, solid circuit design, reasonable component selection, because you got some Sanyo capacitors and name brand parts. Only thing that bugs me is the thermal design and the power design, because they didn't bother to integrate their own power supply. At the same time, it's a valid choice. They may have decided it's cheaper for us to certify this component because it's already certified and we're just modifying it in certain countries like North America, versus trying to certify their entire AC block here and make a bigger PCB. So until next time, peace out.